We'll now talk about something known as parametric vector form. When solving a system of equations, we know we can describe solution sets using a set of equations whenever it has an infinite number of solutions. However, that's not the common way to denote these. It's more common to use this idea of parametric vector form. In this form, we actually write the solution as a linear combination of vectors. And we might be able to best see this using an example. Let's suppose we have this augmented matrix and we want to look at writing the solution. The first row gives us x1 plus 5x3 equal to -2, and the second row gives us x2 minus 3x3 equal to 4. And we know we should solve for our basic variables, where the pivots are, so we should solve for x1 and x2. When we do this, we get x1 is equal to -5x3 minus 2, x2 is 3x3 plus 4, and x3 is any value. Well, there are other ways we can write this. We can write a solution vector x equal to x1, x2, x3, and then we can substitute in what we know for these. We know x1 is -5x3 minus 2, we know x2 is 3x3 plus 4, and we don't know anything about x3, so we just write it as x3. We can then break this up. I'm going to write it as a sum of vectors. One, all the terms that contain the variable x3, and then the other one being all of the constants. We can then factor out the x3 to get x3 times -531 plus -240. And if we use our scalar multiplication and addition, we'll see that this right-hand thing does get back to what we originally started with. In a previous video, when we talked about related homogeneous and non-homogeneous systems, we said that non-homogeneous systems were written as H plus P, where H is the solution to the homogeneous and P is a particular solution. And that's exactly what this is. Any of our variable vectors, that's going to be our H, and then our constant vector is going to be P.